When you look at this picture of a busy street, what are some of the things that you notice are using space? All of these things that you have noticed are elements of a system, the street. Hi everybody, my name is Kate Schweikert, and today we're going to talk about systems engineers who think about elements in a bigger picture all the time. Systems engineering is a large field of engineering with a lot of different components. We will walk you through some of the basics today, starting with an overview, a look at the life cycle of a system, and finally, the impact that systems engineering has on our world. To start off, we'll give you an overview of systems engineering with some examples so that you can start thinking like an engineer. When engineers talk about systems, they are much like the systems in our bodies. For example, we have the skeletal system, circulatory system, respiratory system, and more. Each of these systems has specific functions. The respiratory system allows us to breathe, and the circulatory system moves blood throughout our bodies. All of these subsystems work together to give us all our abilities. As an example of a system that engineers worked on, let's take a look at this shuttle from NASA that went to the moon, Apollo 11. Now, a space shuttle may seem quite different from our bodies, but it also has systems in order to get to space and operate in space. The structural system is like the skeleton of our bodies, but for the shuttle. It creates the shape and includes the walls to keep the astronauts and equipment safe inside. The propulsion system on the space shuttle has an engine and burns fuel, similar to a car, to thrust it upwards. On the inside of Apollo 11, there are even more systems. The astronaut can use these systems while they are in space. There's a communication system so that people on Earth can communicate with the astronauts. This system uses transmitters to send messages and receivers to get messages. There's also a control system, because the space shuttle is full of controls, so astronauts can make sure they're going in the right direction, at the right speed, and that the interior climate is comfortable. The two systems we talked about already are a lot like most systems. There is one big system which is at the top of the hierarchy. Then, within that big system, there are multiple subsystems. Taking one more step down from that, we can have even more subsystems, or we can have individual elements of the system. Sometimes we call these systems of systems, because there are systems contained within larger systems. For example, if we revisit our first example, the system is our body. A subsystem is our respiratory system. Within the respiratory system, we have lungs, which are an element of the system. This is a system hierarchy that I came up with for a school. There are many different subsystems involved here, but I generalized it down to 3: administration, structure, and transportation. Within each of these subsystems, there are more subsystems and elements. Are there any other subsystems or elements you could include here? Systems thinking is a vital skill in this study of engineering. To be systems thinkers, we need to consider the big picture, but also think about how the smaller elements make up that big picture. Once a problem is defined, a systems thinker will look at it from many perspectives and explore all the options. A full understanding will also allow a systems thinker to anticipate difficulties and any consequences, both short and long term. Now that we have the basics on what systems engineering is, we're going to go through the systems life cycle and how we use this to develop and maintain our products. Some of you may already be familiar with the engineering design process, and the systems development life cycle is similar. The life cycle displayed here gives engineers the basic framework of instruction for a systems project. Projects typically start in the concept phase and then work around the cycle. Sometimes this cycle isn't followed exactly, as you may need to go back and make changes in development or production before utilization, but this is a general view of how systems engineers organize their work. Let's explore the idea of developing a bike, which we'll talk about during each phase.
Hi everyone, my name is Jolene. In the concept phase of the systems development lifecycle, when a problem or need is identified, the systems engineers set out to do as much research as they can to develop a knowledge base of the problem area. With this knowledge, they can start assembling their ideas for how to solve this problem. Considering our example, the concept phase is when the need for a new bike design is identified. Do we need this bike for road racing, for mountain biking, or for basic recreational use? The systems engineers then research the different bike frame designs that would make the bike more aerodynamic. They research different tires, brakes, and reflector lights to address performance and safety. This phase is where the engineers get to use their creativity to come up with as many possible solutions to their problem as possible. The more ideas there are to choose from, the better their chances are of creating a solution that has a combination of the best features from each idea. The challenge facing the systems engineers is coming up with ideas that address the stakeholder needs and being able to do it with the resources available to them, whether that be time, money, or existing technology. In our example, the systems engineers bring all of their various bike design ideas to the table. It's during this phase that the systems engineers need to check back in with a stakeholder to make sure they're understanding the needs correctly. Everything they decide on is with the stakeholder needs in mind. After lots of analysis of the proposed solutions and trade studies to see which bike design is better than others and why, the systems engineers must decide on one design to move forward with. During the development of the system, an architecture of the system is generated. Similar to the blueprints of a house being the basis for how a house is built, a system must have blueprints. These blueprints are a communication tool that allow the engineers producing the system to understand what the designers intended when developing the system, so it is important that they are communicated effectively. In terms of our example, this would be the handoff of the detailed bike design to the engineers who will make the bike. These design documents must indicate all of the specific needs, such as the size of the bike, the right sensitivity of the brakes, the number of gears, and the tire pressure allotment. Risk management is an important part of development because if there are high-level risks identified, which are in the red area on the matrix, that are successfully mitigated and either eliminated or lowered to a lesser level risk, which are in the yellow or green areas on the matrix, then the success of the system is much more likely. It also shows that the systems engineers are thinking through the bigger picture and envisioning possible scenarios that the system might find itself in, and what sorts of things may happen as a result of those scenarios. An example of this is, say you are riding your bike down the street, and you know there is a huge pothole up ahead in the road. This is an example of identifying the risky scenario. What's the risk statement? If you hit the pothole while riding your bike, then you could fall off your bike and hurt yourself. If you wanted to avoid that, you could simply steer around the pothole since you know right where it's located. This is an example of avoiding the risk. Alternatively, you could wear a helmet. This is an example of mitigating the risk, or making the impact less severe, since if you hit the pothole and fall off your bike, your head will be protected and you wouldn't hurt yourself as badly. If we apply these concepts to the development of the bike we've been talking about, we could consider risks related to different types of brakes. The bike could have hand brakes or pedal brakes, and each of these have risks associated with them. For example, pedal brakes are engaged by pedaling backwards. This could be challenging to use in an emergency stop situation.
Thank you, Jolene. Once the design is finalized, it's finally time to start making the system. When considering production, most often a manufacturing floor comes to mind, where they're machining and assembling parts, as you can see in the picture. People who manufacture bikes do so in mass quantities, so the process to build it needs to be efficient and easy to repeat. The frame for the bikes are often made from big steel blocks that is drawn into tubes. Once the tubes are made, they are welded together into the bicycle frames we know. People then work on an assembly line to attach gears, handles, pedals, and more. Verification is basically a checklist to go through once the system has been made that checks each requirement and confirms that the system performs the way it is expected to. This is often done with a procedure so that when quality gets involved, they can follow along during the verification process and make sure that the engineer doing the verifying is doing it the way that it's supposed to be done. If we look at our example, this would be when we evaluate our requirements of what the bike needed to have and check that the final product result meets all of those requirements, such as, is the bike capable of riding on rocky dirt roads? If the desired result was a mountain bike, this might need to be verified by testing it on an actual rocky dirt road. Does the bike have reflector lights for safety reasons? This could easily be determined by inspecting the bike. Once the system has been created and checked over to make sure all of the subsystems are integrated together properly, it is time to transition the system to its intended environment. During the utilization phase, the system becomes operational and the end users validate that the system works as they wanted it to. In our example, now that the bike has been properly verified to meet all the requirements, the bicyclist can start riding it. During these initial phases, the bicyclist is validating that the bike meets their expectation by testing it out in real time. Similar to how you go to the doctor for a checkup, systems that engineers work on need to be checked in on. If there is something wrong with the system, the technicians, like doctors, can fix it and make sure it is working properly again. For our example, a bike, once delivered to the bicyclist, doesn't stop there in our system development lifecycle. As the bike is used, it will occasionally need tune-ups, such as if the brake pads get too low or if the tire threads wear too thin, both situations which could result in accidents. A maintenance plan is put into place for the bike to ensure that there is never a time when the bike is being ridden unsafely. There could also be a situation where it doesn't impact the safety, but still needs fixing, such as the kickstand not working. The same maintainers who fix the brake pads and tires could also fix the kickstand. When a system has reached the end of its life, or it is no longer needed, it must be properly disposed of. Depending on the system, sometimes hazardous waste needs to be considered, dangerous chemicals or substances that need to be controlled to reduce the risk of causing harm to the environment. Other times, it is as simple as bringing the system to the dump. However, in the case of certain electronics, they need to be recycled in a special way to ensure a successful retirement or disposal of the system. All of this needs to be considered as early as the concept phase. To conclude our bike example, once the bicyclist no longer has a need to ride the bike, it needs to be disposed of somehow. Ideally, it could be reused for a new owner, thus prolonging the utilization and support phases for the life cycle of this particular bike. Alternatively, the bike could be scavenged for parts that can be reused on other newer bikes. Otherwise, if the bike is damaged beyond repair, it may just end up in the dump. Putting together the basic definitions of systems engineering with the guidance of the development lifecycle, we can begin to see how systems engineering makes a large impact in our world. Sometimes the hardest thing about working in teams is the working part. Having someone to facilitate the interaction between engineers that can't normally communicate is very important, and that's what systems engineers do. They obviously bring their own ideas to the table, but mostly they know about other disciplines so they can help bridge the gaps between them during the development phase. One of the biggest reasons why systems engineering is important is because without it, then a lot of projects would seem too big to tackle. The complex relationships that systems inherently carry are difficult to handle when not looked at it from a systems perspective. It's no surprise that systems develop organically since they are necessary, but very few people understand the workings because they are so complicated. That's where systems engineers come in. Just like a bike is a mode of transportation, there are many others that are much more complex. Things like airlines, buses, trains, all work together in an informal capacity. This is a system, a huge one that encompasses all sorts of different components and relationships, but a system nonetheless. Systems engineers understand the importance of making sure that these components work together seamlessly. Therefore, they aim to improve the systems that already exist and work on making them better. be it that the transportation system across the country, or a new model of jet, or a brand new bike. Thank you so much for listening to our presentation about systems engineering. I hope you learned a lot from it, and maybe some of you will someday be that very engineers that we're talking about today. Have a great day.